Hi everyone, welcome to Miss B Maths Teacher channel and welcome back to lesson 1B integration. So this one is just the second part of lesson 1. In the first part, I have talked about lower and upper rectangles, and we have used 3 intervals to calculate this lower and upper area. So 3 intervals have been used. Pretty much what does it mean? It means that we wanted to calculate the area under this curve between 1 and 4. So, and we have divided this length into 3 equal intervals. So this is the one, second one, and then third one. So, and we have used lower and upper rectangles. So if you haven't seen this video, I would recommend first to watch 1A before you watch 1B. So the area that has been calculated, the lower one was 17 and the upper one was 32. So, and then we mentioned, okay, this is, some sort of okay estimation, but we would like to improve this estimate. And we mentioned about what would happen if we do have more sub-intervals. So instead of having 3 intervals, maybe to have more. So, and this time we're gonna go with having 6, so just doubling. And pretty much if we know that in the first one, each interval here, the width was 1, 1, 1, and now if we're gonna have 6 intervals instead of 2, so pretty much it means we're gonna halve this. We're gonna halve those intervals. So it's easy to calculate when you have nice numbers, so 6 intervals. So it's easy to calculate when you have nice numbers. So, and sometimes you have like too many decimals, or the numbers are not as nice, and it's handy to know how actually this width is calculated. So the width, let's use W, width is equal to, pretty much we know we have to divide this part here, so this length, into 6 equal intervals. So first we have to find what is this length. So if this is 4, this is 1, so the length here is 4 take away 1. So it's 4 from 0 to here is 4, but we don't have all of that, so this part is taken away. That's why we say 4 take away 1. So we can see it's 3, but as I said before, sometimes it's easier just to use the numbers that are given. So 4 take away 1. So I'm just gonna write here 4 take away 1, and then over how many intervals or sub-intervals we want. We want 6. So 4 take away 1 is 3, divided by 6 is half. Pretty much this is now telling us the length or the width of each interval. So it's gonna be half. If this is 1, this is 2. So the next one, it will be 1.5. It's gonna be here. So then we have 2, another half, and then another half, and another half, and another half. So now, in order to find the lower area, so we're gonna do the same what we have done before. Lower one, so we're gonna create rectangles. Again, we're looking, between 1 and 1.5. So we're looking for the minimum value of the graph. So, and it's at this point when x is equal to 1, and then we're gonna have a line across, and we're gonna create one triangle. then same is going to happen for the interval between 1.5 and 2. So the lower the minimum value is at 1.5, line across another right angle, and same. So now we have a 2 and cross, and then we have at 2.5, and then across, then we have a 3 across, and then we have at 3.5, and then across. So you can see now, if you do compare this to lesson 1a, that now we do have more rectangles. So, and now find the area. So area is length times height. So length times height. The height of this rectangle is the same as when what y is equal to when x is equal to 1. So pretty much what we're saying here, length is half. So it's half times f of 1. So, and then plus half f of 1.5, then plus half, and then f of 2 plus half, and then f of 2.5, and then plus I'm just gonna continue here, plus half and f of 3. So this one here, and we have one more, half and f of 3.5. Maybe you can notice that we have so many half is common for every single one. So pretty much we can write this the same, like say half as a common, and then go f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 plus f of 3 and plus f of 3.5. So we can do that as well. So, and then equal to. Now, I'm not gonna do substitution for when x is equal to 1, x is equal to 1.5, x is equal to 2. So I'm just gonna remind you that this f of 1, f of 1, f of 1.5, of 2, 2.5, 3, 3.5, it's pretty much you using this function y is equal x to the power of 2 plus 1, because this is given, and you're replacing the values of x with first 1. So first 1, substitute, then 1.5, substitute, and so on. So what I'm gonna do here, I'm gonna put numbers, but I would like you to check if you have the same for 1, f of 1, which is 2, and has been calculated before anyway. So 1.5 should be 13/4 plus f of 2 we already have from lesson 1a, it's 5, plus f of 2.5 is 29/4, then plus f of 3 it's 10, and plus f of 3.5 is 53/4. So when we calculate all this, so we're gonna have something equal to, or approximately equal to 20 point, this is lower, yeah, 20.375 units squared. So this is the lower one. Now on the next page, we're gonna calculate the upper one, and so using the same graph, oops, that line is just going everywhere. So using the similar, okay, same as before, I should have pre-drawn this, but that's fine. I guess I'm gonna remember next time. I'm just gonna have 1 here, 2, 3, 1, 2, 3, and 4. And now, as we had before, we're gonna have 1 and then 1.5, because we're gonna have 6 intervals. So 3, 2.5, 3.5. So I didn't even write the numbers here. 2, 3, and then 4 here. Okay, so what color do I need? I'm gonna go with red. Now we have 6 sub-intervals, so and each is equal to half. So this is now upper rectangle, so we're gonna create different rectangles, pretty much what we're looking for between, in this interval between 1 and 1.5. So in this interval we're looking for the maximum value of the curve on that interval. So this or this, so we can say this one is higher, so we're gonna create rectangle. Then we're gonna go between 1, we're gonna go between 1.5 and 2, and looking which one is higher, so is this one here, so we're gonna create another one. So same goes between 2 and 2.5, so we're gonna have here 2.5, and again comparing between 2 and 2.5, which value of the curve is maximum. So it's not 2, it's at 2.5, and we're gonna have this line as well. And then you keep going, so you're looking between 2.5 and 3, 3 and 3.5, 3.5 and 4. So you're just doing the same thing. Okay, so this is 3.5. So between here it's upper one, upper one, upper one. Now we have all these angles, and let's calculate now those area. Area upper is equal to, now the same thing is going to happen, so we're going to have maybe if I move a little bit so I have more space. Okay, I'm going to go from here. Area upper, okay, AU is equal to, we have half F of, now this is the height, this one here, this is the height when x is equal 1.5, so it's 1.5 plus half. For the next one between half and 2, so we're looking at this one here when x is equal to 2 plus half, and then it's f of 2.5, and then plus half times f of 2.5 at 3, and then plus half and f of 3.5. So, and I'm still not gonna have enough space here, so 3.5 and plus half times f of 4, is that correct? Okay, so the last one between 3.5 and 4, the maximum is when x is equal to 4. So pretty much the maximum is, I'm just gonna circle in yellow. So maximums are when x is equal to 4, so we have that one. When x is equal 3.5, so we have that one. When x is equal 3, so we have that one. When x is equal 2.5, we have that one. When x is equal 2, we have that one. And when x is equal 1.5. So now equal to, again calculating, as you have seen before, again you can have like half as a common, then everything adding up. So and we can do that, or half, and then we have f of 1.5. Please note you don't have to write this all the time. You can either go with this line here, or the one that you're gonna see now. So you don't have to have both, definitely. So it is, again, I have this line, just gonna get rid of this one here. Yeah, so times f of 1.5, okay, it's common, yes, plus f of 2 plus f of 2.5 plus f of 3 plus f of 3.5 and plus f of 4. So all this calculated should give us something that's going to be equal 27.875 units to the power of 2. Before I move on, just to remind you how we got these values. Actually, what I'm going to do, I'm going to give you one more line here, okay, before we have the final answer. So I'm going to have half. F of 1.5 is 13/4 plus f of 2 is 5, has been calculated already twice. F of 2.5 is 29/4, so you have seen that one as well. F of 3 is 10, f of 3.5 is 53/4, and f of 4 is 17. So all this together now should give us 27.875 units squared. So one more time, what's happening, or how we calculated, how we got those values here. So we are using x equal to 1.5, x equal to 2, x equal to 2.5, x equal to 3, 3.5, and 4, and we substitute all this, of course, at different times. We sub all this into y equal to x to the power of 1, and then you're gonna get, you know, different values. So which is this one, this one, this one, this one, this one, this one. So now what we have, it's again two values. Okay, next page. I'm trying to go to next. Yeah. So what we have now, we have the area is between, I'm just going to write again, lower and upper. And we can see that lower this time was 20.375 and upper was 27.375. Here on the side, just remember, if you can recall, that area when we had only 3 sub-intervals, it was between 32 and 17. So and now when we had more sub-intervals, what actually has happened, the estimate is better. So we now know that the area is, you know, between 20 and 27. So what is happening here? So if we have more sub-intervals, so this area is going to have better estimate. So what will happen? So it would happen with more sub-intervals, with more intervals, however you want to call them. So this number 20 is gonna get closer to, so this is gonna decrease and this one is gonna increase, and they're gonna approach, you know, some, you know, definite interval. Okay, so the area under the curve. So, and this is happening when n, which is the number. What is the n? N is the number of subintervals. Number of intervals. So if we have more, so as the number of subintervals increases, so we can say, okay, n is approaching infinity, so it's getting bigger. So we can say that a lower is, we can say it's approaching a as well. So as n is approaching infinity, a upper is approaching a as well. So I'm not going to use limits at this stage. So I'm just going to go, you know, with, you know, n is approaching infinite number, so it's going to be big. And so what's gonna, yeah, okay, I may mention limits. So limits as n is approaching infinity of al, it's gonna be equal to a, and limit n is approaching infinity of a upper. So more subintervals, we're gonna have the good estimate or calculation of the area under the curve. So this value a is known as definite integral. So definite integral, so of f of x from a to b. So, and we usually this is notation for this from a to b, and we have f of x dx. So, and it does mean this is pretty much what they say, that if f of x is bigger or equal to 0, so if we say here f of x, which is our function, bigger or equal to 0 for all x's less or equal to b and bigger or equal to a, then this integration ab f of x dx is equal to the area under the curve. So let's have a small picture here. So like this, like that. If this is a, this is b, this is your function, y equal f of x, and this is the area under the curve. So pretty much what is this saying here? F of x bigger or equal to 0. Yeah, bigger or equal to 0. This one is bigger, is above the x-axis, and x is between a and b. X is between a and b, so this is lowest a, the highest one. Then integration from a to b, fx dx, is the same as this shaded area. So sometimes you can see here that actually this part is addressed or labeled, this one here. So it said shaded area. Okay, shaded area. Okay, so that would be all for now. I'm hoping this makes sense. Please let me know if you do want another example. So thank you for watching, and talk to you soon. Bye.